Please subscribe to support the channel. When you step outside on a clear night and gaze upward at the stars scattered across the darkness, you're participating in one of humanity's oldest activities. For thousands of years, people have looked at those points of light and wondered what lies beyond them. We see galaxies stretching out in every direction, layer upon layer of cosmic structure fading into the black. But this simple observation leads to a question that has haunted astronomers and philosophers alike. Does this go on forever? Or is there somewhere out there an edge to everything? Does the universe have a boundary, a place where space itself comes to an end? The answer to this question turns out to be far stranger, more complicated, and more beautiful than our ancestors could have imagined. It's a puzzle that sits at the intersection of physics, astronomy, and philosophy, challenging our most basic assumptions about the nature of reality itself. Before we can even begin to answer where the universe ends, we need to be clear about what we mean when we say universe. This might seem obvious at first, but cosmologists have learned to be very precise with their language because they're actually talking about several different concepts that are easy to confuse. When most people think about the universe, they imagine everything that exists, the totality of all space, matter, energy, and time. Scientists call this simply the universe without qualifiers. But there's another concept that's equally important for our discussion, something called the observable universe. This is the portion of the total universe from which light has had time to reach us during the entire history of the cosmos. These two things, the universe and the observable universe, are fundamentally different, and much of the confusion about cosmic boundaries comes from mixing them up. The observable universe has a definite edge, a boundary beyond which we cannot see. The actual universe, on the other hand, might have no edge at all. It could extend infinitely in all directions, or it could curve back on itself like the surface of a sphere, having a finite size, but no boundary or edge in the traditional sense. When astronomers talk about finding the end of the universe, they're usually discussing one of three things: the edge of the observable universe, the potential geometric limits of space itself, or the event horizons created by cosmic expansion. Each of these represents a different kind of boundary, and each tells us something profound about the cosmos we inhabit. To understand why there's a limit to what we can observe, we need to think about the fundamental speed limit of the universe. Light, the fastest thing in existence, travels at approximately 186,282 miles per second, or about 300,000 kilometers per second. This seems instantaneous in our everyday experience. When you flip a light switch, the room illuminates immediately as far as your perception is concerned. But on cosmic scales, even this incredible speed becomes limiting. When we look at the sun, we're seeing it as it was about 8 minutes ago, because that's how long it takes light to cross the 93 million miles between the sun and Earth. The nearest star system, Alpha Centauri, is about 4.37 light-years away, meaning we see it as it appeared more than 4 years in the past. This time delay becomes more dramatic as we look deeper into space. When we observe a galaxy 10 million light-years away, we're seeing light that left that galaxy 10 million years ago. We're literally looking backward in time, seeing that galaxy as it existed in the distant past. This means that astronomy is uniquely positioned among the sciences. While biologists study present-day organisms and chemists observe reactions happening in real time, astronomers are time travelers of a sort, observing events that occurred millions or billions of years ago. The telescope becomes a time machine, and the farther out we look, the farther back we see. This relationship between distance and time creates a natural horizon, a boundary beyond which we cannot see, not because there's nothing there, but because the light from those regions hasn't had enough time to reach us yet. The universe, according to our best measurements, began approximately 13.8 billion years ago in an event we call the Big Bang. You might think this means we can see out to a distance of 13.8 billion light-years, since that's how long light has been traveling through the cosmos. But the reality is more complicated, more interesting, and reveals something profound about the nature of space itself. The observable universe, the sphere of space from which light has had time to reach us, has a radius of about 46.5 billion light-years in every direction. This makes the observable universe roughly 93 billion light-years across, a number that immediately seems paradoxical. How can we see objects 46.5 billion light-years away when the universe is only 13.8 billion years old? The light from those objects has only been traveling for 13.8 billion years. So shouldn't they be at most 13.8 billion light-years away? This apparent contradiction reveals one of the most important discoveries in cosmology. The universe itself is expanding, and the space between objects is stretching. Imagine you're watching a photon of light begin its journey towards Earth from a distant galaxy. That galaxy might have been, say, a few million light-years away when the photon started its journey. The photon travels through space at the speed of light, covering vast distances. But while the photon is traveling, space itself is expanding. The distance between the photon's starting point and Earth is growing larger even as the photon moves towards us. It's like running on a treadmill that's slowly accelerating. You're moving forward, but your destination is also moving away from you. Eventually, after traveling for billions of years, the photon reaches Earth and enters our telescopes. But in that time, the galaxy that emitted the light we're now seeing is now much farther away than the distance light could have traveled in the age of the universe. This expansion of space is crucial to understanding cosmic boundaries. Space isn't just a static stage on which cosmic events play out. It's dynamic, growing, stretching, carrying galaxies along with it. The most distant objects we can observe are now about 46.5 billion light-years away due to this expansion, even though we're seeing them as they appeared much closer and much earlier in cosmic history. This creates a boundary to the observable universe, not because there's nothing beyond it, but because light from regions farther away hasn't had time to reach us yet. The universe, according to our best measurements, could be and probably is much more universe out there beyond this horizon. We just can't see it yet. And as we'll discuss later, thanks to the accelerating expansion of the universe, there are regions we may never be able to see no matter how long we wait. But there's another boundary that's even more fundamental to our observations, a wall in time beyond which our most powerful telescopes cannot peer. This boundary is marked by something called the cosmic microwave background radiation, and understanding it requires us to think about what the universe was like in its earliest moments. In the first few 100,000 years after the Big Bang, the universe was extremely hot and dense. Matter existed as a plasma, a soup of free electrons and atomic nuclei bouncing around in intense radiation. This plasma was opaque to light. Photons couldn't travel very far before being absorbed or scattered by the free electrons, much like how you can't see through fog. The universe was essentially one vast fog bank of glowing plasma. Then, about 380,000 years after the Big Bang, something remarkable happened. The universe had expanded and cooled enough for electrons to combine with atomic nuclei to form neutral atoms, primarily hydrogen and helium. This event, called recombination, made the universe suddenly transparent. Light could finally travel freely through space, without constantly being scattered. The photons that were released at this moment have been traveling through the universe ever since, and we can detect them today as the cosmic microwave background radiation, or CMB. This radiation comes from every direction in the sky, a faint glow, filling the universe with a temperature of about 2.7 degrees above absolute zero. The cosmic microwave background represents the oldest light we can possibly see. It's a baby picture of the universe, showing us what conditions were like when the cosmos was just 380,000 years old. But it also represents an absolute boundary to our observations. We cannot see beyond this wall of light. Not because nothing exists before it, but because before recombination, the universe was opaque. Any attempt to look further back in time with electromagnetic radiation hits this barrier, It's like trying to see through the surface of the sun. The light we detect from our star comes from its outer layers, the photosphere, and we cannot see directly into its interior because the material is opaque to visible light. Similarly, the CMB is the surface of last scattering, the shell of the ancient universe from which light could finally escape. This ancient light does more than just mark a boundary in time. The patterns and fluctuations in the cosmic microwave background contain an enormous amount of information about the universe's composition, age, and geometry. Scientists had studied this radiation in exquisite detail using satellites like COBE, WIMAP, and most recently, the Planck spacecraft. These observations have revealed tiny temperature variations in the CMB, fluctuations of only a few millionths of a degree. These variations represent the seeds of all cosmic structure, the quantum fluctuations in the early universe that would eventually grow into galaxies, clusters of galaxies, and the vast cosmic web of matter we observe today. But perhaps most remarkably, these fluctuations tell us about the shape of space itself. This is where our question about the end of the universe takes on a geometric character. When we ask whether the universe has an edge or boundary, we're really asking about the topology and geometry of space. Is space flat, extending infinitely like an endless plane? Does it curve back on itself like the surface of a sphere, creating a universe that's finite but has no edge or boundary? Or does it curve the other way like a saddle or Pringles potato chip? This surface has negative curvature, curving away from itself. A universe with this geometry would also be infinite, extending forever, but the relationship between distance and area would be different than in flat space. Parallel lines would diverge rather than remaining parallel, and triangles would have angles that sum to less than 180 degrees. Our universe exists in 3 dimensions of space, rather than 2, which make visualizing these geometries more challenging. But the mathematics works the same way. A 3-dimensional space can have positive curvature, like the 3-dimensional analog of a sphere surface, a structure called the 3-sphere. It can be flat, extending infinitely in all 3 dimensions, where it can have negative curvature, a hyperbolic geometry that extends infinitely, but with its own unique properties. The question of which geometry describes our universe is not philosophical speculation. It can be measured, and the cosmic microwave background provides the tool to do so. The key lies in those tiny temperature fluctuations in the ancient radiation. These variations have a characteristic size, determined by physics in the early universe. By measuring the apparent size of these fluctuations across the sky, scientists can determine the geometry of space. If space has positive curvature, features in the CMB would appear larger than expected, magnified by the curvature of space itself. If space has negative curvature, they would appear smaller. And if space is flat, they would appear at exactly the size predicted by early universe physics. It's similar to how a triangle drawn on a sphere would have angles that sum to more than 180 degrees, while a triangle in flat space would sum to exactly 180 degrees. The measurements from the Planck satellite and other instruments have provided an answer with remarkable precision. Our universe appears to be flat to within about 1% margin of error. The angles of cosmic triangles sum to 180 degrees as far as we can measure. The apparent size of features in the cosmic microwave background match exactly what we would expect in flat space. This is one of the most important discoveries in the history of cosmology, because it tells us something profound about the extent of the universe. If space is truly flat, not just approximately flat in the regions we can measure, but fundamentally flat everywhere, then the universe is almost certainly infinite in extent. An infinite universe is a concept that challenges our imagination. It means there is no edge, no boundary, no wall at the end of space. No matter how far you traveled, you would never reach a place where space ends. There would always be more universe beyond. But infinity brings its own strange implications, paradoxes that sound like science fiction, but may be inevitable consequences of truly endless space. If the universe is infinite, and if the laws of physics are the same everywhere, and if matter is distributed roughly uniformly on the largest scales, then an infinite universe must contain infinite galaxies, infinite stars, and infinite planets. More strangely still, in an infinite universe with finite possible arrangements of matter, everything that can happen must happen somewhere and must happen infinitely many times. This includes exact copies of Earth, of our solar system, of you reading these words right now.
Somewhere out there beyond our cosmic horizon, in regions we can never see or visit, there may be perfect duplicates of our planet, with people living lives identical to ours, or almost identical with tiny variations. There would be versions of Earth where you made different choices, where history unfolded differently, where the quantum dice rolled other ways. This isn't speculation or philosophy, it's a mathematical consequence of infinite space combined with finite complexity. This idea troubles some physicists because it seems untestable, unfalsifiable, more like metaphysics in science. We can never travel to these duplicate Earths, never verify their existence. They lie forever beyond our cosmic horizon. Yet the infinity of space seems to require them if our understanding of physics is correct. It's a reminder that answering the question about where the universe ends opens up as many mysteries as it solves. The absence of an edge brings its own conceptual challenges. But we haven't yet addressed another crucial aspect of cosmic boundaries. The fact that the universe isn't static. Space isn't just sitting there, it's expanding, and this expansion changes everything about how we think about cosmic horizons. The expansion of the universe was one of the most revolutionary discoveries of the 20th century. In the 1920s, Edwin Hubble observed that distant galaxies were moving away from us, and the farther they were away, the faster they were receding. This wasn't because the galaxies were moving through space away from us, rather, space itself was expanding, carrying the galaxies along with it.
For decades, astronomers assumed this expansion must be slowing down. After all, the universe is filled with matter, and gravity pulls everything together. The expansion should be gradually decelerating, slowed by the gravitational attraction of all the matter in the cosmos. The question was whether there was enough matter to eventually halt and reverse the expansion, causing the universe to recollapse in a big crunch, or whether the expansion would continue forever, just gradually slowing down. In the 1990s, two teams of astronomers set out to measure this deceleration by observing distant supernovae, stellar explosions that serve as cosmic distance markers. What they found shocked the scientific community and earned them the Nobel Prize. The universe's expansion wasn't slowing down at all. It was speeding up. Distant supernovae were farther away than they should be if the expansion had been constant or decelerating. Something was pushing the universe apart, accelerating the expansion of space itself. This mysterious something has been named dark energy, though that's more of a label for our ignorance than an explanation. We don't know what dark energy is, where it comes from, or why it exists. We only know that it makes up about 68% of the total energy content of the universe, far more than ordinary matter, far more than dark matter, and it's causing space to expand at an accelerating rate. This accelerating expansion has profound implications for cosmic boundaries. In a universe that was just expanding at a constant rate, or slowly decelerating, any event anywhere in the universe would eventually become visible to us. We would just have to wait long enough for the light to reach us. But in an accelerating universe, this is no longer true. There are regions of space that are moving away from us so fast that light leaving them now will never reach us. The expansion of space between us and those distant regions is accelerating fast enough that the light, despite traveling at the ultimate cosmic speed limit, can never close the gap. This creates a different kind of boundary called the cosmic event horizon. Think of it like being in a boat on a river that's flowing faster than you can row. Even if you row upstream with all your strength, you're still moving downstream because the current is stronger than you're rowing. Similarly, light from beyond the cosmic event horizon is traveling toward us at the speed of light, but space is expanding so rapidly that the distance between us and that light is actually increasing. These photons will travel forever, never stopping, never slowing, but never reaching us because the space between us and them is growing faster than they can traverse it. Currently, the cosmic event horizon is about 16 billion light-years away. Galaxies farther than this are receding from us faster than light can travel. Not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding that rapidly. This means that about 94% of the observable universe is already beyond our cosmic event horizon. We can see these distant galaxies because we're seeing ancient light that left them billions of years ago when they were closer to us. But any light leaving those galaxies today will never reach us.
We are seeing their past, but we will never see their future. They have crossed the boundary and, in a sense, left our universe forever, even though they still physically exist. As time goes on and the expansion continues to accelerate, more and more galaxies will cross this event horizon and disappear from view. Galaxies that are currently within our observable universe, galaxies we can see right now, will gradually fade and redshift away, their light stretched to longer and longer wavelengths until they become undetectable. In the far future, trillions of years from now, assuming the current acceleration continues, any observer in our galaxy will look out and see only the local group of galaxies, our gravitationally bound cluster. Everything else will have been carried away by expansion beyond the cosmic event horizon, leaving those future observers in what appears to be a small, lonely universe surrounded by darkness. They will have lost the evidence of the Big Bang. The cosmic microwave background will have been redshifted to unmeasurably long wavelengths. They will have lost the evidence of cosmic expansion, since all distant galaxies will have disappeared. An astronomer in that distant epoch would have no way to discover the truths about the universe that we've learned in our time. It's a sobering reminder that our position in cosmic history is special, not because we're at the center of anything, but because we happen to live at a time when the evidence of the universe's nature is still visible. But what about the ultimate fate of this expansion? If dark energy continues to accelerate the expansion, will the universe eventually tear itself apart? Some theoretical scenarios suggest this is possible. If dark energy grows stronger over time rather than remaining constant, it could lead to a fate called the Big Rip. In this scenario, the accelerating expansion becomes so extreme that it overwhelms all other forces. First, galaxy clusters would be torn apart, then individual galaxies would be shredded. As the expansion accelerates further, solar systems would be disrupted, planets torn from their orbits, eventually even molecules would be ripped apart, then atoms and finally even atomic nuclei would be destroyed, as space expands so rapidly that nothing can hold together. This would be the ultimate end of cosmic structure, a universe torn to pieces by its own expansion. This sounds like science fiction horror, but it's a real theoretical possibility, being seriously considered by cosmologists. The good news, if we can call it that, is that current observations suggest dark energy isn't strengthening in this way. It appears to be a cosmological constant, a fixed energy density of space itself that doesn't change over time. If this remains true, the universe will continue expanding and accelerating forever, but won't experience a big rip. Structures held together by gravity, like galaxies and solar systems, will remain intact even as the space between separate gravitationally bound systems expands. But we've only been measuring dark energy for a few decades. We're extrapolating the fate of the cosmos over trillions of years based on measurements spanning less than a human lifetime. There's still much we don't understand. The mystery of dark energy and the accelerating expansion leads us to consider even more exotic possibilities about the nature of cosmic boundaries. What if our universe, everything we can see and even everything beyond our cosmic horizon, is just one region of something much larger? What if there are other universes out there, separate domains of space and time with which we can never interact? This idea, once relegated to science fiction and philosophy, has become a serious subject of scientific discussion under the umbrella term of the multiverse. The concept of multiple universes arises naturally from several areas of theoretical physics. One of the most compelling connections comes from cosmic inflation, the theory that the universe underwent a period of exponentially rapid expansion in the first fraction of a second after the Big Bang. Inflation was proposed to solve several puzzles about the observed properties of our universe, including why space appears so flat and why the cosmic microwave background has almost exactly the same temperature in all directions. If the early universe expanded by an enormous factor in a tiny instant, regions that started out in contact would have been stretched far apart, explaining why distant regions of space have similar properties. They once were close enough to interact and equilibrate. Inflation does an impressive job of explaining what we observe, and it's become the standard framework for understanding the early universe. But inflation, if it happened at all, probably didn't happen just once and then stop. The quantum physics governing the inflation field suggests that inflation, once started, is eternal in most regions. Imagine the early universe as a rapidly inflating space where quantum fluctuations cause inflation to end in some regions while continuing in others. The regions where inflation ends become normal, slower expanding universes like ours. But the regions where inflation continues keep inflating exponentially. And within those regions, new pockets where inflation ends will constantly form. Each pocket becomes a separate universe, a bubble of space that stops inflating and begins evolving under more familiar physical laws. This eternal inflation scenario suggests that our observable universe is just one bubble in an infinite foam of universes. Each bubble would have its own Big Bang, the moment when inflation ended in that region, and the energy driving inflation converted into matter and radiation. Each bubble universe might be infinite in extent itself, but the bubbles would be separated by regions of eternally inflating space. Because space between bubbles is expanding exponentially fast, bubbles can never collide or interact once they've formed. They are causally disconnected, separate universes in the most complete sense of the word. No light, no information, no influence of any kind can pass from one bubble to another.
Even more intriguingly, the properties of physics might be different in each bubble universe. The laws of physics as we know them appear to depend on certain fundamental constants and parameters: the mass of the electron, the strength of gravity, the charge of the proton, and dozens of others. We don't know why these constants have the values they do. They appear arbitrary, fine-tuned, often precisely balanced in ways that seem improbable. For example, if gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were slightly different, atoms couldn't form. Our universe appears remarkably well suited for complexity in life, and this seems puzzling if the constants were simply chosen randomly. But in a multiverse scenario, these constants might not be the same everywhere. Different bubble universes might have different values for these fundamental parameters. Some bubbles might have physics similar to ours, others radically different. Most bubbles might have physics that doesn't allow complex structures to form at all. No atoms, no stars, just uniform soup or empty space. We find ourselves in a bubble with suitable physics not because all bubbles are like this, but because we could only evolve in a bubble where the physics permits complexity in life. It's a selection effect. We necessarily observe a universe compatible with our existence. This is called the anthropic principle, and it remains controversial because it seems to give up on finding a deeper explanation for why physics is the way it is, replacing explanation with selection from a vast ensemble of possibilities. The multiverse raises profound questions about the nature of scientific explanation and what we can hope to understand about existence. If there are infinite universes with all possible properties, then asking why our universe has the particular properties it does becomes unanswerable except through anthropic reasoning. We're here because the constants happen to be right in this bubble. In another bubble with different physics, other forms of existence might wonder about their physical laws. This seems to some scientists like giving up, admitting we can't find deeper principles governing reality. To others, it seems like the natural conclusion of our best theories combined with honest reasoning about what we can and can't explain. But there's a more fundamental question. Can we test the multiverse hypothesis? If other universes are causally disconnected from ours, lying forever beyond any possible observation or experiment, is the multiverse idea even scientific? The concern is that science should deal with testable predictions, with claims that can be verified or falsified through observation. If the multiverse is real but undetectable, have we crossed from physics into metaphysics? Some physicists argue yes, that multiverse theories are interesting speculations but not testable science. Others argue that we can test multiverse theories indirectly by testing inflation and by looking for subtle effects that might arise if our bubble universe is part of a larger structure. For instance, if inflation is eternal and produces multiple bubble universes, very occasionally two bubbles might collide during their formation, before the space between them expands too much. Such a collision would leave an imprint on the cosmic microwave background, a disk-shaped region of temperature anomalies in the ancient radiation. Scientists have searched for such collision signatures in CMB data from the Planck satellite and so far haven't found convincing evidence.
This doesn't rule out the multiverse. Collisions might be extremely rare or might have occurred in regions we can't observe, but it's an example of how multiverse theories can make testable predictions despite seeming untestable at first glance. Another potential test comes from the overall structure and properties of physics in our observable universe. If the multiverse is real and fundamental constants vary between universes, we can ask statistical questions about what kinds of universes should be common and what should be rare. If our universe's properties fall into an expected range for the multiverse, that provides weak support for the theory. If our properties seem bizarre or impossible in the multiverse framework, that would be evidence against it. This kind of reasoning is subtle and indirect, far from the clean experimental tests of traditional physics, but it may be the best we can do when dealing with questions this vast. The multiverse discussion connects to another mind-bending idea about the nature of cosmic boundaries, the holographic principle. This idea comes from attempts to understand black holes and quantum gravity. Black holes have event horizons, surfaces beyond which nothing can escape, not even light. Information that falls into a black hole seems to be lost forever, disappearing behind the event horizon. But quantum mechanics says information can't be destroyed. This contradiction, the black hole information paradox, led physicists to reconsider what information really means and where it's stored. The resolution, still being worked out, seems to involve a strange property of space itself. All the information about what's inside a black hole, all the complexity of everything that's fallen in, is somehow encoded on the two-dimensional surface of the event horizon. The three-dimensional interior of the black hole is in some sense described completely by information on its two-dimensional boundary. This is called the holographic principle because it resembles a hologram, a two-dimensional surface that contains a complete three-dimensional image. Physicists like Leonard Susskind and Gerard 't Hooft have proposed that this principle applies not just to black holes, but to the entire universe. All the physics happening in three-dimensional space might be completely described by information encoded on a two-dimensional boundary. The universe we perceive, with its depth and volume and three-dimensional structure, might be a kind of projection or hologram from this lower dimensional description. This doesn't mean the universe is fake or illusory. The three-dimensional description is perfectly valid for all practical purposes. But at the deepest level, reality might be fundamentally two-dimensional, with our three-dimensional experience emerging from that more fundamental structure. What does this mean for cosmic boundaries? If the holographic principle is correct, the ultimate boundary of the universe might not be a three-dimensional edge or horizon, but a two-dimensional surface on which all of reality is encoded. In some versions of this idea, the boundary is at infinity, an infinitely distant surface that nonetheless contains all possible information about the interior. In other versions, connected to the cosmic event horizon we discussed earlier, the boundary might be the accelerating expansion horizon, with everything we can ever observe described by information encoded on that receding surface. These ideas are still highly speculative in our areas of active research in quantum gravity and string theory. Speaking of quantum mechanics, we should consider how quantum effects might influence the structure of space at the largest scales and what this means for boundaries. Quantum mechanics describes the behavior of matter and energy at the smallest scales, governing atoms, particles, and forces. But quantum effects might also be relevant for understanding space and time themselves. Some theories suggest that space is not continuous but made up of discrete units, quanta of space smaller than anything we can currently measure, but finite nonetheless. This is similar to how matter is made of atoms rather than being continuous. If space is quantized, then zooming in far enough would reveal a grainy, discrete structure rather than smooth continuity. Loop quantum gravity is one theoretical framework exploring this possibility. In this approach, space is woven from tiny loops and networks of quantum geometry, with volume and area coming in discrete chunks. The smooth space we experience emerges from these quantum building blocks the way a fabric appears smooth but is woven from individual threads. If this picture is correct, it might affect our understanding of cosmic boundaries. An infinite universe might contain a countably infinite number of spatial quanta rather than an uncountably infinite continuum. The distinction seems philosophical, but it could matter for questions about what exists at the largest scales and how to count or measure infinities in cosmology.
Quantum mechanics also introduces fundamental uncertainty into cosmic structure. The tiny fluctuations we see in the cosmic microwave background, the seeds of all galaxies and cosmic structure, originated as quantum fluctuations in the inflation field. Microscopic quantum uncertainties were inflated to cosmic scales, becoming the variations in density that gravity would amplify into galaxies and clusters. This means the large-scale structure of the universe, The positions and properties of galaxies stretching across billions of light years ultimately arose from quantum randomness. Different regions beyond our cosmic horizon might have different large-scale structures because quantum fluctuations would have produced different patterns there. In a sense, quantum mechanics ensures variety across the infinite universe if the universe is indeed infinite. But let's return from these theoretical heights to something more concrete. What our observations actually tell us about cosmic boundaries? We've discussed the theoretical frameworks and possibilities, but what do our best telescopes and instruments actually show us? The cosmic microwave background observations from Planck and earlier missions have given us the most detailed map of the early universe ever made. These observations confirm that space is flat to high precision, supporting the idea that the universe is infinite. They show that the universe is homogeneous and isotropic on large scales, looking roughly the same in all directions, which is consistent with our understanding of cosmic structure. But there are some anomalies in the data, patterns that aren't fully explained by our standard cosmological models. There's a slight asymmetry in the cosmic microwave background, with one half of the sky showing slightly larger fluctuations than the other. There are also some unexpected alignments in the largest scale patterns, sometimes called the axis of evil because of how unexpected and troubling they are for standard cosmology. These anomalies could be statistical flukes, the kinds of unusual patterns that inevitably appear occasionally in random data. Or they could be hints of something deeper, signatures of physics beyond our current models, or perhaps even effects from the larger structure of the universe beyond our observable region. Some researchers have suggested these anomalies might be evidence of a multiverse, perhaps showing the influence of other bubble universes on our own during the earliest moments of cosmic history. Others have proposed they might indicate the universe has non-trivial topology, maybe looping back on itself in some dimensions even if it appears flat overall. Still others think they're simply artifacts of how we analyze the data, or genuine flukes that will disappear with more precise measurements. The point is that even our best observations leave room for mystery and multiple interpretations. We're pushing against the limits of what we can measure, and the data at these extremes are ambiguous enough that different theoretical frameworks can accommodate them. Future observations might help resolve some of these questions. Next-generation telescopes, both ground-based and space-based, will observe the universe in greater detail and to greater distances than ever before. Projects like the James Webb Space Telescope are already revealing galaxies from when the universe was very young, just a few 100 million years after the Big Bang. Future radio telescope arrays like the Square Kilometer Array will map the distribution of hydrogen gas across cosmic history, revealing how large-scale structure formed and evolved. These observations will test our models of cosmic expansion, dark energy, and the ultimate geometry of space. Gravitational wave astronomy, the ability to detect ripples in space-time from violent cosmic events, might shed light on questions about cosmic boundaries. We're now able to detect gravitational waves from colliding black holes and neutron stars, and future detectors might be sensitive enough to detect gravitational waves from the inflationary epoch itself. Such primordial gravitational waves would carry information about the universe when it was just a tiny fraction of a second old, potentially telling us about the physics of inflation and whether eternal inflation and the multiverse are real. This is speculative. We don't yet know if primordial gravitational waves are detectable, but it's an example of how new observational techniques might illuminate questions that seem permanently beyond our reach. Still, we must confront the possibility that some questions about cosmic boundaries might be fundamentally unanswerable through observation. This isn't a defeatist position, but a recognition of the limits imposed by the speed of light, cosmic expansion, and the finite age of the universe. There are regions of space we will never be able to observe, no matter how long we wait or how advanced our technology becomes. If the universe is infinite, the vast majority of it is and will remain forever beyond our horizon. We can theorize about what's out there, we can extrapolate from what we see in our observable region, but we cannot directly verify those extrapolations. This is a kind of cosmic humility, accepting that reality might be vastly larger and more complex than the portion we can access. This limitation raises deep philosophical questions about the nature of scientific knowledge. Traditionally, science advances by proposing theories and testing them through observation and experiment. But what do we do when regions of reality are in principle unobservable? Can we claim scientific knowledge about the unobservable universe?
Some philosophers and scientists argue no, that science should confine itself to testable claims about the observable world. What lies beyond our cosmic horizon is metaphysics or speculation, not science. Others argue that we can reason scientifically about the unobservable universe if our reasoning is based on well-tested theories that apply to the observable region. If the laws of physics are the same everywhere, which is a fundamental assumption of cosmology, then we can use those laws to make inferences about regions we can't see. There's also the question of whether the unobservable universe is unobservable for contingent reasons or fundamental ones. If we can't see beyond the cosmic event horizon because the expansion of space is accelerating, that's a contingent fact about our current universe. If dark energy behaved differently, if the expansion were decelerating instead, then regions currently beyond the event horizon might eventually become observable. But if we can't see beyond the surface of last scattering, marked by the cosmic microwave background, that's more fundamental. The universe was opaque before recombination, and no form of electromagnetic radiation can penetrate that barrier. However, other messengers might. Neutrinos and gravitational waves both stream through the opaque early universe, carrying information from even earlier times. Future neutrino telescopes or gravitational wave detectors might let us peer beyond the CMB, seeing back to the first seconds or even the first fraction of a second after the Big Bang. These considerations show that the boundaries we face in observing the universe are complex and multi-layered. There's the particle horizon, the distance light has traveled since the Big Bang, though this is complicated by expansion. There's the event horizon created by accelerating expansion, beyond which we'll never see. There's the surface of last scattering from recombination. Each represents a different kind of boundary with different implications for what we can know. And then there are the theoretical boundaries we've discussed, the possible edge of space if the universe has positive curvature, or the boundaries between bubble universes in eternal inflation, or the holographic boundary encoding all information about the interior. These boundaries stack and interweave in ways that challenge our intuitions about where things end and what it means for something to have a boundary. Living in a universe that may have no edge, no center, and possibly no end forces us to reconsider humanity's place in the cosmos. For most of human history, we place ourselves at the center of creation. Earth was the center of the universe, with everything else revolving around us. Copernicus and Galileo showed that Earth orbits the sun, not the other way around, displacing us from the geometric center. But we still thought the sun might be at the center of the universe. Then we learned our sun is just one of hundreds of billions of stars in the Milky Way galaxy, located out in the galactic suburbs, not at the center. And the Milky Way turned out to be just one of hundreds of billions of galaxies stretching across space with no special location or significance.
This process of removing ourselves from any privileged position has been called the Copernican principle, or the principle of mediocrity. We should not assume we're special or central. Our planet, our star, our galaxy, our position in space and time should all be typical, average, unremarkable. This principle has been enormously fruitful in science, guiding us away from anthropocentric thinking toward more objective understanding. But it also leads to a kind of cosmic insignificance. If the universe is infinite, then Earth is not just non-central, but utterly typical, one of infinitely many planets and infinitely many galaxies, perhaps even one of infinitely many exact copies of Earth scattered across infinite space. Some people find this perspective depressing or nihilistic. If we're infinitesimally small in an infinite cosmos, if there are infinite copies of us elsewhere, does anything we do matter? But there's another way to view it. The fact that we exist at all, that the universe has given rise to consciousness and intelligence and beings who can contemplate these questions, is remarkable regardless of how many times it happens. The infinite universe doesn't diminish the value of any particular instance of experience or existence. You are not less significant because there might be other versions of you in unreachable regions of an infinite cosmos. Your experiences, your choices, your connections with others are real and meaningful in this region in space, in this moment of time. Moreover, the question of cosmic boundaries connects to deep questions about existence itself. Why is there something rather than nothing? Why does the universe exist at all, with whatever boundaries or extent it has? These questions go beyond physics into philosophy and perhaps theology. Physics can tell us about the structure and evolution of the universe, about how it began, if it had a beginning, about whether it's finite or infinite, about how it will end if it has an ending. But physics cannot, at least not yet, and perhaps not ever, tell us why any of this exists in the first place. The question of cosmic boundaries touches on this mystery because if the universe is infinite, it seems to need no external cause or creator. It simply is, extending endlessly, perhaps eternal in time as well as space. But if the universe is finite, if it has boundaries, we're tempted to ask what lies beyond those boundaries? What caused the universe to have the particular size and shape it does? These questions have occupied philosophers and theologians for millennia. Ancient Greek philosophers debated whether the cosmos was finite or infinite, with Aristotle arguing for a finite cosmos with Earth at the center, and atomists like Democritus imagining infinite space filled with infinite worlds. Kant argued that pure reason alone could not determine whether the universe was finite or infinite, that both positions led to contradictions when pushed to their logical extremes. He saw this as evidence that space and time were not properties of things themselves, but rather structures of human perception and understanding. Modern cosmology has given us tools Kant could never have imagined for approaching these questions empirically. We can measure the geometry of space, observe the expansion of the universe, map the distribution of matter across billions of light years. We've learned things about cosmic boundaries that would have astonished and perhaps troubled the ancient philosophers. Yet in some ways, we've come full circle, confronting the same fundamental puzzles about infinity, boundaries, and existence that occupied ancient thinkers. We're better informed, armed with data and mathematics, but the deepest questions remain profound and perhaps unanswerable. The accelerating expansion of the universe adds urgency to our attempts to understand cosmic boundaries because it means our window for observation is limited in a way earlier cosmologists didn't realize. When Einstein first applied his equations of general relativity to the universe as a whole, he found that space could not be static. It had to be either expanding or contracting. Einstein initially found this so disturbing that he added an extra term to his equations, the cosmological constant, to force the universe to be static. He later called this his greatest blunder, after Hubble discovered that the universe was indeed expanding. Ironically, the cosmological constant has made a comeback as a possible explanation for dark energy and the accelerating expansion. The very term Einstein introduced to prevent cosmic evolution might be causing the acceleration that will eventually hide most of the universe from view. This means that in some sense, we live in a golden age for cosmology. We can see the cosmic microwave background. We can observe how the expansion rate has changed over cosmic history by looking at distant supernova and galaxies. We can map the large-scale structure of the universe. Future civilizations, trillions of years from now, if any exist, will have lost this evidence. The CMB will have redshifted beyond detectability, distant galaxies will have disappeared beyond the event horizon, and the local group of galaxies will be all that remains visible, isolated in a dark, apparently static universe. Those future astronomers will have no way to discover the Big Bang, no way to know the universe is expanding, no way to learn the truths about cosmic history and structure that are obvious to us. This raises an unsettling question. What evidence might we be missing? Are there cosmic phenomena or eras that have already disappeared from view? Information about the universe's boundaries or structure that is no longer accessible from our position in space and time. The CMB shows us the universe at 380,000 years old, but we can't see earlier with electromagnetic radiation. Are there crucial clues about cosmic boundaries in that inaccessible early era? The cosmic event horizon is already receding, carrying galaxies and regions of space beyond our ability to ever observe them. What information is being lost? We can only work with what's accessible to us, but it's humbling to consider that we might be missing crucial pieces of the puzzle, evidence that would make clear answers to questions we're still debating. The nature of dark energy itself is one of these open questions with profound implications for boundaries. We know dark energy is accelerating the expansion, and we can measure its effects on cosmic structure and the expansion rate, but we don't know what it is. Is it truly a cosmological constant, a fixed energy density of empty space itself? Is it a dynamic field, something that changes over time and might behave differently in the future? Is it a sign that our understanding of gravity breaks down on cosmic scales, requiring modifications to general relativity? Each possibility has different implications for the ultimate fate of the universe and the nature of cosmic boundaries. If dark energy is a cosmological constant, the universe will continue expanding and accelerating forever, asymptotically approaching a state called de Sitter space. In de Sitter space, the cosmic event horizon settles at a fixed distance, and anything beyond that distance remains forever out of reach. The universe would continue existing indefinitely, with isolated gravitationally bound structures like our local group of galaxies persisting while the space between separate structures continues expanding.
Eventually, on timescales of googles of years, even protons might decay and black holes evaporate through Hawking radiation, leaving empty, expanding space with vanishingly dilute radiation. This would be a cold, dark, lonely end, not a dramatic finish, but a gradual fading away.
If dark energy is dynamic, the possibilities multiply. It might decay over time, eventually becoming negligible, and allowing the expansion to coast or even reverse if there's enough matter in the universe. This could lead to a big crunch, with the universe collapsing back to a singularity, perhaps bouncing into a new cycle of expansion. Or, dark energy might strengthen, leading to the big rip we discussed earlier, where even atoms are torn apart by runaway expansion. Or, it might do something entirely unexpected, transforming into a different form of energy, triggering a phase transition that fundamentally alters the nature of space and physical laws. We simply don't know, because we don't understand what dark energy is. Some theoretical physicists have suggested that dark energy might be connected to the vacuum energy of quantum fields permeating space. Quantum mechanics predicts that even empty space should be filled with virtual particles constantly popping in and out of existence, contributing energy to the vacuum. When you calculate how much energy this should contribute, you get a number that's roughly 10 to the power of 120 times larger than the observed dark energy density. This is perhaps the worst prediction in the history of physics, off by 120 orders of magnitude. Something is wrong, either with the calculation or with our understanding of how vacuum energy relates to cosmic expansion. Solving this cosmological constant problem, explaining why the vacuum energy is so much smaller than predicted, yet still positive, is one of the deepest puzzles in theoretical physics. The answer might involve new physics, perhaps connected to quantum gravity or string theory. In string theory, the fundamental building blocks of reality are not point particles, but tiny vibrating strings of energy. The theory requires extra dimensions of space beyond the three we experience, with those extra dimensions curled up small enough that we don't notice them in everyday life. String theory also predicts an enormous number of possible vacuum states, different ways the fields and dimensions can be configured, each with different values for the cosmological constant and other physical parameters. This landscape of possible vacua might connect to the multiverse, with different bubble universes corresponding to different points in the string landscape. If this picture is correct, our universe's particular value of dark energy isn't determined by some deep principle, but is effectively random, selected from the landscape of possibilities. We observe the value we do because only universes with small positive cosmological constants can form galaxies and stars and life. Too large, and expansion would have been so rapid that matter never clumped together to form structure. Negative, and the universe would have recollapsed before stars could form. Our value, while seemingly arbitrary, falls in the narrow range compatible with observers existing to measure it. This is anthropic reasoning again, explaining observations through selection effects rather than fundamental principles. Critics of this approach argue that it's giving up on finding deeper explanations. If we invoke the multiverse and anthropic selection, we can explain almost any observation by saying it had to be that way for us to exist. This makes a framework unfalsifiable, and therefore unscientific in the traditional sense. Proponents counter that if this is how reality actually works, if we do live in a multiverse where parameters vary, then anthropic reasoning is not giving up, but accepting reality. The question is whether there's a way to test these ideas beyond their ability to accommodate what we observe. One approach is to ask whether our universe's properties are typical among the subset of universes that could support observers. If we find that some observed value is extremely unusual even among observer-compatible universes, that would suggest the multiverse explanation is incomplete or wrong. So far, some properties, like the cosmological constant, appear to be reasonably typical if you accept anthropic selection, but others remain puzzling. The fine-tuning of the universe for life involves many parameters, and whether they can all be explained anthropically remains debated. Another approach is to look for direct or indirect evidence of other universes. We've mentioned searching for collision signatures in the cosmic microwave background. Another possibility involves looking at the distribution of properties across our observable universe.
If different regions had slightly different physical constants or showed evidence of different vacuum states, that might indicate we're seeing effects from a multiverse structure. So far, observations show the laws of physics are the same everywhere we can measure, but we're limited to our observable region. The vast majority of space, if the universe is infinite, remains beyond our reach. This brings us back to the fundamental tension in answering where the universe ends. We have multiple frameworks and possibilities, each suggesting different kinds of boundaries or lack thereof. We have the observable universe with its clear boundary at the cosmic event horizon and the surface of last scattering. We have the possibility of an infinite flat universe with no spatial boundary at all. We have the potential for positive curvature, creating a finite but boundless universe. We have eternal inflation, producing bubble universes separated by inflating space. We have the holographic principle, suggesting reality might be encoded on a lower dimensional boundary. And we have the accelerating expansion, carrying more and more of the cosmos beyond our reach of observation. What we know for certain is limited but profound. We know the observable universe is about 93 billion light-years across, containing hundreds of billions of galaxies, each with hundreds of billions of stars. We know space appears to be flat on large scales, suggesting it might be infinite. We know the universe is expanding and that this expansion is accelerating due to something we call dark energy, but don't really understand. We know that there are fundamental horizons beyond which we cannot see, regions of space that are and will remain permanently inaccessible to our observations. We know that the cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang, but blocks our view of earlier times. What we don't know is equally profound. We don't know if the universe is truly infinite or merely much larger than the observable region. We don't know if there are other universes beyond ours or if bubble universes exist in a multiverse structure. We don't know what dark energy is or how it will evolve in the future. We don't know if space is continuous or quantized at the smallest scales. We don't know if there are dimensions beyond the 3 of space and 1 of time that we experience. We don't know if the laws of physics are the same everywhere or vary across the cosmos. We don't know why the universe exists at all, or why it has the particular properties it does. These unknowns aren't failures of science, but frontiers of inquiry, questions we're actively investigating with new observations and new theoretical frameworks. Every answer we find seems to raise new questions, deeper and more subtle than what came before. This is how science progresses, not by reaching final answers, but by refining our questions and expanding our understanding of what we don't yet know. The question of where the universe ends has evolved from a simple geometric puzzle into a complex tapestry of physics, cosmology, and philosophy, touching on the nature of space, time, causality, and existence itself. For anyone looking up at the night sky and wondering what lies beyond, the answer is both more mundane and more extraordinary than our ancestors could have imagined. Beyond what we can see are more galaxies, more stars, more space, stretching out for distances that dwarf even our vast observable universe. If space is infinite, it goes on literally forever, with no edge, no boundary, no end. If it curves back on itself, it forms a cosmos that is finite, but still has no edge where it ends, just as the surface of Earth is finite, but has no boundary where it ends. And interwoven through all of this is the mysterious dark energy, accelerating the expansion, carrying distant regions beyond our ability to ever observe them, creating horizons that partition the universe into regions that can never communicate or interact.
We exist in a particular place and time, able to observe a finite sphere of space surrounding us, a bubble of observability in a cosmos that may extend infinitely beyond. We're like inhabitants of an island in a vast ocean, able to see to the horizon but unable to determine if the ocean is finite or infinite, if there are other islands beyond our view, if our island is typical or unusual. Yet from our limited vantage point, using mathematics, physics, and careful observation, we've learned extraordinary things about the structure and history of the cosmos. We've traced the evolution of the universe back to fractions of a second after the Big Bang. We've measured the geometry of space across billions of light years. We've detected the faint afterglow of creation itself in the cosmic microwave background. We've discovered that the expansion of space is accelerating, due to a mysterious energy we don't understand. These discoveries answer some questions about cosmic boundaries while opening up new mysteries. The observable universe has a boundary, but it's not an edge where space ends. It's a horizon beyond which we cannot see, determined by the finite speed of light and the finite age of the universe. The actual universe, the totality of all that exists, might have no boundary at all if space is flat or negatively curved, extending infinitely in all directions. Or it might be finite but boundless if space has positive curvature, curving back on itself. Or it might just be one bubble in an infinite multiverse of bubbles, each constituting its own universe with its own beginning and possibly its own physical laws. The accelerating expansion means that even in an infinite universe, there's a practical boundary to what we can influence or observe. Galaxies beyond the cosmic event horizon are forever out of reach, not because they stop existing, but because space between us and them is expanding too rapidly for any signal to cross. This creates islands of causality, regions within which events can influence each other, but which are isolated from distant regions. Our observable universe is one such island, and it's shrinking in terms of the fraction of the total universe we can access. More and more of reality is slipping beyond our horizon, disappearing from view, carrying with it information about the nature and extent of cosmic structure. This might seem depressing, the idea that most of reality is unknowable, and that the portion we can observe is decreasing over time. But there's something profound and even beautiful about the fact that we exist at a time when the universe is still revealing its secrets. The cosmic microwave background is still visible, distant galaxies still observable, the evidence of the Big Bang and cosmic expansion still present in the sky. We're fortunate to live in an era when the universe's history and structure can still be read from the light reaching our telescopes. We're asking these questions about cosmic boundaries at precisely the epoch in cosmic history when they can be answered observationally. Future civilizations, if any exist, trillions of years from now, won't have access to this evidence. They'll be isolated in a seemingly static, dark cosmos, unable to discover the truths about expansion, the Big Bang, or the larger structure beyond their local group of galaxies. The question of where the universe ends is thus both answered and unanswered. We know where the observable universe ends, at the cosmic event horizon and the surface of last scattering, boundaries created by cosmic expansion and the finite speed of light. But we don't know where the universe itself ends, whether it has an end at all. The best evidence suggests space is flat and likely infinite, extending forever with no edge. But we can only measure this within our observable region. The vast majority of space, if the universe is infinite, remains forever beyond our reach, unknowable through any observation or experiment we can conceive. This is a profound realization about the limits of human knowledge. There are questions we can ask, questions that have definite answers, questions about objective reality that we nonetheless cannot answer through observation. The extent of the universe beyond our horizon is one such question. We can reason about it, extrapolate from what we see, build theoretical frameworks, but we cannot directly observe the answer. This doesn't make the question meaningless or unscientific. It just means we must be humble about the limits of empirical knowledge and careful about distinguishing between what we can observe, what we can reasonably infer, and what remains speculation. Living in such a universe, one that might be infinite, that's certainly vast beyond comprehension, that contains structure and beauty at every scale, from quantum to cosmic, should inspire both humility and wonder. Humility because we're such a tiny part of the whole, occupying an infinitesimal fraction of space, existing for a brief moment in cosmic time, able to observe only a small bubble of the total reality. But also wonder because, despite these limitations, we've managed to understand so much. We've figured out that the universe began in a hot, dense state and has been expanding for 13.8 billion years. We've measured the geometry of space across billions of light years.
We've traced cosmic evolution from the first moments after the Big Bang through the formation of atoms, stars, galaxies, planets, and life. We've discovered that most of the universe is made of mysterious dark matter and dark energy that we're only beginning to understand. And we've learned that the universe might have no edge, that space might extend infinitely, that everything we can see is just a tiny fraction of what exists. This is perhaps the most important answer to the question of where the universe ends. It doesn't end. It goes on and on and on, beyond anything we can observe or imagine, an infinite or near-infinite cosmos in which we're privileged to exist, to observe, to wonder, and to ask these impossible, beautiful questions about the nature and extent of reality itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.